Your textbook contains two more rules for writing electron configurations. Rule 2 is that each orbital can accommodate two electrons, each of opposite spin. Rule 3 is that electrons filling the p, d, and f subshells don't pair until they have to. Electrons repel each other and will occupy their own orbital if they can. These two rules are best applied to what are known as orbital diagrams. Orbital diagrams are based on electron configurations, but orbital diagrams give more information about electron spin. On this slide, we have the electron configurations for boron, carbon, and nitrogen. To the right of each electron configuration is the orbital diagram. Notice that in the orbital diagram, each orbital is represented by a box, and that orbitals that are in the same subshell, like the three p orbitals in the p subshell, are connected. These orbital diagrams show the opposite spin of electrons in the filled 1s and 2s orbitals. Boron, carbon, and nitrogen have filled 1s and 2s orbitals. Now let's look at the p subshell. Boron has one electron in the 2p subshell. This is also known as an unpaired electron. Carbon has two electrons in that 2p subshell. However, the second electron does not pair with the first electron. Since there are three orbitals in the p subshell, the second electron goes into a different orbital. Both electrons are spin up. Carbon atoms have two unpaired electrons. Nitrogen has three electrons in the 2p subshell, and each electron is in a separate orbital. Nitrogen has three unpaired electrons. Once we get to oxygen, which has four electrons in the 2p subshell, we need to start pairing. Oxygen has two unpaired electrons in the 2p subshell. Fluorine has one unpaired electron in the 2p subshell, and neon, with a full p subshell, has no unpaired electrons. Orbital diagrams allow us to clearly see how many unpaired electrons there are in an atom.